Welcome to the Bytecode, where we look at smart contracts with the people who wrote them. I'm your host Shafu, and today's episode is with GT, who's gonna walk us through Deck Mk2, which is a optimized smart account. JT, thanks for taking the time, man.
Yeah, thanks for having me.
Yeah, so why don't you briefly introduce yourself, introduce your project, and then we can directly dive into the code.
Cool. Yeah, so just little background on me. I come from originally fintech, doing mobile dev, like mobile apps and a little bit of back end. Eventually worked my way over to crypto through ETH Global's hackathons. And then I've been here for about 2 years, give or take. And I mostly just do open source things these days. Working on different libraries like Sol. I did a little bit with Sol80, Soulmate, things like that. And yeah, so this thing is called the Deck Mk2. So the Deck is a nod to William Gibson's Neuromancer and pretty much all of cyberpunk literature these days. They're essentially these like computers that sort of hackers use to interface with like the net, right? Like that's kind of like where that descends from, right? And kind of the idea with this, right, is like in the sort of hardware community, cyber decks are like these little scrappy, like thrown together computers that you can interact with the internet and things like that through generally like terminal based. And that was kind of the idea behind the Ether deck. Was I wanted to kind of just throw together my own like smart account, something that doesn't necessarily optimize for specific ERCs or specific like user experiences, just kind of something that I thought would be like a really cool way to interact with the chain. Now, the first iteration of this, the original Ether deck, was it was a monstrosity. This thing was written in Huff. It had this like wild ABI encoding scheme. It was an M of N multisig and just all kinds of wild logic behind it. That it was kind of confusing for anybody that wasn't like in the know on it. And the naming conventions are pretty weird too. But so this one's the Mark II, and so the Mark II is it's in Solidity, pretty much exclusively inline assembly for the business logic. And it's no longer an M of N, it's just a smart account, right? So the idea is like ideally, like what I'm planning on doing with this personally is like I'm probably just going to go ahead and move like the majority of the funds and the majority of my like on-chain actions like to this wallet, in time once audits and things like that come through. Um, but yeah, so here's a little bit about like what the Ether deck is, like what it can do. So this is sort of the core contract. It's got a handful of functions you can call in it. You can run a call, which basically just makes the Ether deck call out to something like a target, right? You can run things in batch, so you can do sort of multi calls through your own smart account. You can set dispatchers, either a singleton or in batch. And then what that dispatcher does is anytime that call data comes to the Ether deck, either through like an external call or through like a transaction being initiated, if the selector doesn't match run batch, set dispatch, or set dispatch batch, it actually like falls back into this sort of module system where if there's an address assigned to a selector, then it dispatches that with a delegate call, right? So it's a way of extending the functionality of the Ether deck. So like there's like a ton of mods. We'll go through all of them, right? But there's like flash mod, there's like revoke mod, all these kinds of things, and it basically just allows you to extend this thing indefinitely. So the storage layout on this on the core deck itself is like very very simple. You have a mapping, which is your dispatcher, right? That essentially maps like a 4-byte selector to a target address. You have a runner, which is essentially the owner of the account, right? Runner is also a sort of nod to the old like cyberpunk literature, right? That talks about the people that interface with these decks are usually like net runners, or the word that they use for like going and doing something, right, is they're like going on a run, they're doing a run, right? So that's kind of where like the naming comes from with all of this. And there's a little bit about the ABI, how it's laid out, these kinds of things, what it logs. We won't go too deep into this yet because we're actually going to go and look into the code here in a second. Same thing with events. Now for the mods, again, we'll do a dive into like every single one of these, but we have some really cool ones here. So one is a bribe mod. This essentially allows you to bribe some external party to run transactions on the runner's behalf. So it's sort of like delegating, certain actions based on some kind of incentive that you can give for them to do that. Creator mod allows you to deploy contracts from the deck. So that's either with create or create two. You can also pre-compute addresses to make sure that you're getting, those nice like crazy like leading zero addresses and things like that. You have the Flash mod, which is ERC 3156 compliant, so it does flash loans for like arbitrary tokens. You have the flatline mod, which is essentially a dead man switch. So, if you haven't checked in with the deck after a certain amount of time, the flatline mod allows basically anybody to run this function called contingency, right? And that contingency function basically switches the runner to like somebody that you've delegated to be the sort of like inheritor of the contract, right? So if something happens, if you go offline, if you can't access your deck for an extended amount of time, then you can set this to like a friend or family member or something like that. The mass revoke mod is essentially a panic button, right? So it's kind of like revoke.cache, I think it is, where you can just like mass revoke like all kinds of tokens, but with this you can do it in a single transaction. You have the mass transfer mod, so this could be for an airdrop. This could also be a sort of panic button, right, where you just need to pull all the funds out of your Ether deck at once. We have mod 4337, which is ERC 4337 compliant. That one's still pretty minimal, kind of work in progress on that one. The storage mod is a mod for reading and writing storage slots in batch. Of course, this has to be authenticated because storage rights. And then the two-step transition mod, which is kind of like two-step ownable, but essentially it's just for transitioning, from one runner to the next in a sort of two-step process. We also have a mod registry. Again, we'll look into that. That basically just registers addresses and names. And then so some security considerations, just talks a little bit about like how we can do storage layouts with all these different mods without getting any collisions between them. And then there's still like a lot of invariants and assumptions that need to be documented in general, right? So that's going to be done here relatively soon. But with that, let's go ahead and dive into the code. So we'll switch over to VS Code here. This is the Ether deck. And this is like the core deck that everything else gets registered through. We have one event, this dispatch set, and that allows you to index and reason about like which selectors are set to which addresses and things like that. So we have, again, like it was mentioned before, there's the dispatch and the runner. These are public, so you can just call these and read information from them. By default, whoever deploys the deck is the runner, and so that's got a couple of really cool implications. One is if you just deploy this thing yourself, then automatically you're the runner. It's pretty straightforward, pretty simple. But the plan is to also have a sort of factory that allows you to deploy these decks and sort of in the same transaction, it'll go ahead and configure your deck for you, right? So you can specify which mods you want. If you want any special storage slots written like off the bat, then by having the factory deploy it, the factory is the runner for the duration of the transaction. So it does all of that, and then it transitions, that like sort of authority out to you from there, right? So the run function, it's pretty straightforward from a high level. All this thing does, right, is it takes a target and a payload, and it, basically just forwards that, right? It runs the call from the deck. It's also payable, so we can actually just use the message value instead of having to put, like a U256 value in here and use up more call data on it. But yeah, so so before I get too much into the business logic here, there's a couple of like design principles behind this that you're going to kind of see throughout. So one, every opcode it occupies a single line. This is just for simplicity because you see some of these like deeply nested structures that don't really make a whole lot of sense, and it's like very hard to see like what's happening in terms of control flow. So every sort of like operation gets its own line, right? We try to like pack everything like that. We also defer checks as much as possible. So instead of having like, check if this, revert if not, check if this, revert if not, check if this, revert if not, right? Instead, you can just compose all of those into a single Boolean and then check that, somewhere towards the end, right? So you want to check everything all at once towards the end because these are all atomic anyway, right? So it doesn't really matter that, like in this case, we're checking the success well after we do the call, right? But that doesn't matter because it's all atomic anyway, right? So the call isn't actually complete. So, so now diving into the business logic a bit, we have check, just make sure you're the runner, right? We cache that as a success value. We're going to copy the payload straight to memory, and then from there, we're going to go ahead and execute the call. And so that call execution, is pretty straightforward. It just starts at slot 0. By the way, this is like not, by Solidity standard, this isn't memory safe, right? So you wouldn't want to like inherit this contract and then like call this a run function internally because this actually will like overwrite things like the free memory pointer. But the whole idea behind this stuff, right, is that like the code ends at the end of the function. like in assembly, which means there's nothing else that's happening in Solidity behind the scenes, after that. Like that is the terminal code path, right? And so because of that, you can actually safely overwrite like all these values that Solidity tells you not to. Just don't put it as like memory safe, right? Because if you do that, that's I think that's actually one of the few cases of like undefined behavior in Solidity right now. So definitely just make sure you like in those code paths. But anyway, so we execute the call. Pretty straightforward. We forward the gas. We make it to the target. We forward basically the entire like this is message.value in high level Solidity. This is our like payload. It's where it is in memory, and then sort of the convention with calling something in assembly is if you don't know how big the return data size is, you don't actually specify like where return data goes, and you don't specify how big it is. You just set them to 0, and then you can do that after the call, right? And so that's where we do this, which is return data copy, and then we basically just copy everything that came back from that call, just put it into memory, and then from there we check if it was successful. If so, we return, and if it failed, we revert, right? All we do is bubble up that data. You're going to see this in Open Zeppelin, and I think Solidity does the same thing, right? Where essentially like when you make this call out to like a proxy contract or to anything like this on a low level, you can just bubble up that return data, and if it reverted, then you're basically bubbling up revert data, right? Something else that you're going to see a lot in here, like I mentioned before, whenever you compose these sort of like success booleans, they pretty much all start like this, right? So like logically what this is doing is like we get a boolean that says like are these equivalent, right? Like is the call with a runner, and then separately we want to run this call, which call returns a boolean, right? If it succeeded, it returns 1. If it fails, it returns 0. And so we essentially just do an and operation against that, right? So we say like what this actually means, like what if success do this means is that if both this and this are 1, then we return, right? Because those both need to succeed for it to go through, right? So you're going to see a lot of that throughout the deck as well. Oh, and in terms of documentation, every line of assembly, which is another reason everything has to be online. Every line of assembly has an associated documentation with it, right? So everything should be made like as clear as possible what every line of code does. Now run batch. Sorry,
Yeah,
go ahead.
GT, I actually have a question. If you scroll up, okay, I get it that, okay, you're combining each Boolean and then you're checking it in the end. But why don't you check, like line 47 could be above return data copy, right? There isn't anything that happens to success before that, right?
Right. So the reason for this is like we want to have the return data in memory before we decide to return a revert, because in both cases we're actually returning, or in both cases we're bubbling up whatever came back from the last call, right?
Mm.
So by reverting from slot 0, right, and with a size of return data size, we're basically just like after the call happens, we take whatever comes back from it, we put it into memory, and then we decide if we want to return that or we want to revert that. Right. So like what we could do, right, is we could just like take that out and we could put that, essentially like here, right? And then we can do the same thing here. So it's essentially just kind of saving on code size, right? Like this shouldn't change execution cost, but like this is functionally the same as this because no matter what, we're copying the return data into memory.
Mm.
And yeah, so next one is essentially the same thing, just doing it in batch, right? So we have like a couple of arrays. And so, yeah, really quickly we do, again, the runner check, right? Make sure that the caller is a runner. Then we do a little bit of variable allocation. Now this is, there's a couple of things in here that are like sort of opinionated design decisions, which I'll explain more in depth in a second. But we compute the like pointers for the next target, the next value, and the next payload. And these 3 variables are actually going to get incremented on each iteration in the loop. Right? And then this targets in basically just computes like where is the end of the targets array, which we'll use for the like break condition in the loop. And then there's some other checks in here that make sure that the length of the targets and the length of the values and the length of the payloads are all equivalent, right? And so before we go into that, here's some of the opinionated things. One, you could have these success like compositions all just kind of like grouped together. Functionally, this doesn't really make a difference, right? Because either way, these booleans are going to get composed. This is strictly like code style. Like I like the let, and then the success is here, and then everything else here, and then some of the other ones you'll see there's like memory rights as well, but it's just kind of like grouping sort of the colors of the code together, right? Like there was this I forget. I think she's like a Ruby dev that did this like that did these like talks at these conferences a while back about code styling and like simplification of code, right? And she says do the squint test, right, where you squint to the point that you don't see the words anymore, you just see the colors and the structure, right? And in terms of structure, you want like as little indentation as possible, and you want sort of these groupings of colors to go together, right? So your lets are all together, your compositions are together, your memory rights are together, et cetera, et cetera. And then there's some other things in here, like for example, like mul ox20. This is essentially multiplying something by 32. There are cases in here where okay, let me back up for a second. So one of the things in the style guide, like pretty much the first thing in the style guide is or like sort of the design principles of this code, right? Is like we want it to be high function, but we want form over function still, right? So it's like everything should be reasonably optimized, but when it boils down to like code aesthetics over optimization, choose code aesthetics, right? Because code is read way more times than it's written, so it's important for this thing to be like something that people can like intuitively look at and somewhat reason about, right? So like one of the really cool things here, right, is like I'm sure like the optimizers that are watching this thing are shouting about how you can actually replace multiplication by 32 with shift left by 5. Which is just like this cool little like cheeky optimization that basically just says if you multiply something by 32, you can actually just do a bit shift, and bit shifting is cheaper than multiplication in the EVM, right? But as it turns out, the Yule optimizer is also aware of this, and so there's a simplification rule that does that for you, right? So even though this is like mul 32 here, it gets converted into the optimal thing at compile time. So it's functionally no different, right? Like gas wise, it's no different. But this makes a lot more sense intuitively, that it's like, okay, we're adding an offset to this length value times times 32, right? Like that kind of makes sense. It's like, okay, things are 32 bytes, et cetera, as opposed to like doing the shifting. So there'll be little things in there like this where like there are like known optimization rules that if doing the sort of de-optimized version allows for like better form, but it's not going to matter at compile time anyway, then we tend to lean towards form there. And so diving into the sort of like meat of this loop, right down here, your pointer increments, right? So that's pretty straightforward. We can ignore that. Throughout here, we have the break condition. So in Yule, if you're not aware, the way that you do a sort of infinite loop is with this syntax where normally you have like your precondition and your like post action and your Boolean check in here, right? But if you just do this actually just creates an infinite loop, right? So this is effectively like a while true loop. And so what that does is it allows us to like actually define the break logic inside of the loop. And I think there's some like optimization implications here. Like somebody told me about some really cool thing that like by doing this it removes some like Yule boilerplate, but yeah, so we have our check in here, right, which basically says like, okay, like if the target pointer is at the end of the target's array, then we'll just go ahead and break. We're done with the loop. Otherwise, we have to do this little computation to get like the way that like call data is laid out here with these payloads. The way that call data is laid out is you have a pointer to the target's array, you have a pointer to the values array, and then you have a pointer to the payloads array. Right. But then if you go to the targets array, it's just target, target, target. You go to the values array, it's value, value, value. But in the payloads array, it's different because it's an array. It's a dynamic array of dynamic bytes, right? So there's a pointer to the payload array, and then the payload array is actually an array of pointers that then go to the payloads, right? So it's kind of just like this, you gotta work your way down the line to get to it, right? So yeah, essentially what we're doing, right, is like we go from we go from like the start of this array, and then we're like loading this pointer that allows you to go and find like exactly where the actual payload starts, right? It's just a lot of like pointer black magic and Solidity's ABI system, but yeah. So from there we can get our payload, we can get our payload length, and then we're doing this call data copy operation that basically just from those pointers that we just computed and from that length we just found, we're pulling that into memory, and we always put things leftmost in memory, right? Like earliest in memory as possible. A lot of the operations around the ether deck center around minimizing memory usage as much as possible, right? Because memory eventually expands quadratically. It takes a long time for it to get to that point, but we don't know how big of a payload this thing's going to be operating on, right? Like we want to optimize for like a wide array of use cases. So minimizing memory usage is really important and sort of a recurring theme in the ether deck. So up here, we do this like pointer arithmetic. We get our payload copied to memory. And then this piece, this is like caching this variable is really just like a style thing, because if we did this, then it would bleed over the line and it would make it multi-line and blah, blah, blah. So anytime that, putting the entire operation on a single line would sort of break the line, then we'll break that out. We'll put that into two separate lines just so it's a bit cleaner there. But we get our target and we make our call here, which looks pretty similar to what it did in the run function. The only difference here is that we actually have to break apart the values, right? Because the total call value should be the sum of all the values in the in the values array, right? So in this case, like we can't just forward like all of the value. We actually have to break it apart, unfortunately. So we get a little call data load in there, but same thing as before. We're like composing that success, right? So making sure that success boolean is always composed into a single value. And then again, those little pointer increments. So then once this loop is done, right, this loop is going to go until the target pointer is at the end of the target's array. Once it's there, we break the loop. And then from there, that's when we check our success, right? So sort of a similar thing as before. The only difference here is we're not copying return data to memory. We're actually just returning like 0, right? And the reason for this is like if you wanted to return all of these, you would have to return, essentially like an ABI encoded bytes array, and that actually incurs like massive memory cost for a couple of reasons, right? Like, so one of these is, so this is actually a really, really hard problem because none of the payloads have a known size, at compile time, right? It's only at runtime that we're aware of how big the payload size is, right? So if you like visualize memory, you have, you would copy your payload, right? You would run your call, and then you need to copy return data somewhere, right? But then you need to copy the next payload, which might be bigger than the last, right? And then maybe that return data is bigger than the last, right? So like the way that Solidity would do this, right? Like in a sort of high level sense, is it would allocate new memory for the payload, right? It would allocate memory for the return data array, right? And then I think actually, God, how would they do this? They would probably have to set up like the array is like a series of pointers, and then those pointers like go to each instance of like the return data. Basically, it creates like a huge chunk of memory where Solidity doesn't deallocate memory. So like all the payloads are sitting somewhere in memory, and then all of the return data is sitting somewhere in memory. And then there's even a chance that like you have to sort of encode like everything once again, right? So you just get like this huge memory blow up in here. So yeah, basically the easiest way to do this, right, was to just say like, don't copy any return data, just do this, right? And tools are getting better, off chain that allows you to pull some of that return data and stuff like that now. But yeah, so that's kind of the bulk of what's going on here. Is essentially we're just doing the same thing as run. We're just looping over a series of targets, values, and payloads. So next up we have set dispatch, right, which we're not actually using. One second. Right. So this is our dispatch variable, which this is, sorry, one second. Sorry about that. Hopefully we can edit that out. But, right. So with the dispatch here, right, we have this public function, it's a mapping of bytes forward to address. Now there's like a cheeky optimization in this where, I'm not actually using the dispatch slot name. I'm actually kind of just computing these things on the fly. And so what the optimization here actually is the way you would encode something in the dispatch mapping is you put the selector in memory. So 32 bytes of the selector, padded, and then you have 32 bytes of the storage index, right? So like where in storage, this thing sits. And so that storage index is determined by the contract at compile time. Basically, it starts at 0. And then it increments for every full variable that occupies a whole word. There are these other rules of like, if two variables are small and they can be packed into a single word, then they will. But only in like certain conditions. It's a whole thing. It's really complicated. But for this, because not only are we at the top of the inheritance tree, and it's the first variable, we know that the storage index is 0, right? And I think it's documented in here. It might be up at the top, but basically just says that like if you're going to rearrange the variables here, if you're going to do some inheritance, you need to be aware that this dispatch thing has to be in slot 0. The reason for that is, so in this function, we check to make sure the caller is the runner. This is the only thing that can possibly fail. Like, this is only the only failing like revert path in the business logic. So we just go ahead and revert here. We don't do any caching. So what this would actually look like, in its entirety would be something like this, right? Where like this is the storage index. Like I think we can actually say dispatch.slot. I think. Yeah, that looks good. So this is essentially what it would look like, right? Where we store the selector in memory at slot 0. We store the dispatch slot, right, which is a storage index, at slot or at index 32, and then we hash that, right? So we hash, starting at slot 0 for 64 bytes. We hash that together, and we use that as a storage slot, for this target, right? But because this is 0, we can assume that since this is an external function and this is the first thing that's touching memory, right, then we know that this is going to be 0, right, in the 32 slot, right? So we don't actually have to write that at all. We can just omit it, right? Now that's kind of a little unhinged. Like you probably shouldn't rely on that being 0 in like most cases, right? But in this case, because like this is the only external function, it's not being inherited. This is a final contract, blah, blah, blah. We can make assumptions about, that thing being 0, right? But yeah, so we check that it's 0. We, lay out these variables in memory. We hash them together, and then we store that target in storage, and then we log an event, right? And so a little bit about this log here, right? This is the dispatch set event, right? And so what this actually is, in high-level Solidity, right, is you have the dispatch set event, you have an indexed selector, and you have an indexed target, right? But in assembly, this is actually log3. It uses the log3 opcode because the first topic of every Solidity event is the hash of the event selector, right? So what that actually is like you would take this value here, just like this, and you would essentially hash that, right? You can I do this with cast usually, right, which is one of Foundry's tools, but you hash that together, and then that creates this, right? This big 32-byte value, and that's your first topic. And your second topic is a selector, and then your third topic is a target, right? These first two little bits is for like any unindexed topics in an event. They actually just sit in memory, and then you just log like a blob of memory or a chunk of memory, right? So we're not logging any like non-indexed arguments, so we don't have to deal with that at all. Again, topic 1 is the selector of the event, or the sort of like hash of the selector of the event. Second topic is the selector that we're assigning, and the third is the target that we're assigning. And so same thing in set dispatch batch. We have, again, so in this case, we actually want to compose a success because oh, wait a second. This can go away. Sweet. Yeah, that was just like a duplicate of what's happening here. But yeah, so we actually can like break this out into a variable this time because there's two separate checks, right? One is making sure that the caller is the runner, and then the other is making sure that the lengths of the arrays are equivalent, right? Because if they're not, we get some weird like undefined behavior. Yeah, so we do that check, right? So we say like, essentially what we can sort of break this into, right, is we say like if, like so the is 0 and, right, is basically saying like if any of these are 0, then we throw, right? So we say, if the caller does not equal the runner, or the or the selectors and target lengths don't match, then we throw, right? There's like this like optimization rule, and I think actually Yule has this as well. But essentially, it's if not A or not B is the same thing as if not A and B, right? So yeah, that little I don't know, Boolean kung fu there, but basically, yeah, what it's doing is checking both of those together and then throwing if either of those conditions are false. So next we do the pointer computation, or the pointer caching, which we've seen before. That's just going to show us like where we are in the array. We're computing the end of the selector's array. Again, same thing as before. We just say if the selector pointer is at the end, then we just go ahead and break. From here, we're loading these variables. We're actually caching them on the stack because we're going to use them twice. Once in the actual storing operation, and then once in the event log. But we pull the selector, we pull the target. Same thing as before, right? We put the selector in memory implicitly. Memory at index 32 is empty, so we can go ahead and hash that, and we can store, the target at that actual hash. We do our event log, which again, same thing as before, and then we increment our pointers and just run it through, right? And then, at the end of this, of course, it halts, right? So, basically doing the same thing as set dispatch. It's just doing an array of them, so you can kind of configure, all the selectors in a mod like all at once. Now, our fallback is a pretty weird one. There's some weird stuff going on here. So, okay, so out of context of ERCs, just like purely what should this behavior be, right? Intuitively, we would think, okay, we check to see if a selector is set, right, for the dispatcher. If it is, we dispatch it with a delegate call, right, because that means that the runner of the deck has set this, right? If not, then we should probably just do nothing, right? Like we don't want to do something if like a random selector comes in and there's no address assigned to it, right? Because it's clearly something that the runner didn't intend to be run against. So intuitively, you would say, okay, if the selector doesn't match, let's just go ahead and like halt, right? We don't even have to throw. We can just halt and just say like, we received this call. We don't really know what it does. Let's just leave it be. Don't mess with it. Don't touch it. Just go ahead and halt execution and hand it back up. Tell them it's fine, right? Now that's cool, except you get this weird situation of, there's a handful of ERCs, most notably 721 and 1155, where if the recipient of a transfer is a contract, it has to implement this special function, right? And I think we can actually dive into this really quick. So when you do safe transfer from, right, there's some stuff in the specification here that basically says that they have to be an ERC 721 token receiver, and that's this here, right? So you say you have to implement this interface, and you have this function, that has this like selector that matches all of this stuff, and it's going to take all this call data, and then what it should do at the end is it should actually return bytes 4, right? And what it's telling you to return is essentially the selector, right? So the bare minimal receiver interface for a 721 or 1155 says, don't do anything special with this, just take the selector and return it back, right? And so that's pretty straightforward, right? And like for most contracts, like it kind of makes sense. Like personally, I disagree with this abstraction, right? But this is something that this is something that this is something you have to take into account with like let's say you transfer it to like some kind of protocol, right, that doesn't accept ERC 721. Like that's a problem because now you've lost your NFT to it, right? But smart accounts are different because in a smart account, you can kind of just do whatever, right? Like it's generalized, but there's no way to tell ERC 721 like, hey, I'm a generalized smart account. I can do whatever I want, which means I can also handle this in like a simple way. So it always just does this. If there's code there, just require that they return the selector, right? A little bit obnoxious, but essentially, like what we're doing here, right, is there's a couple of optimizations in here, but from a high level, like what we're actually doing is actually let me show you a I think this might be easier to like reason about. So there's differential tests for all of these things, right, where we do like a de-optimized version of everything. So it's both good for testing, and then it's also good for looking at like what actually is happening here, right? So from a high level, like what it's supposed to do, right, is we check the selector, right, those first 4 bytes. We say like, is an address registered to this, right? If it's not, then we return the selector, which I'll explain in a second. If there is an address set though, right, then what we need to do is we need a delegate call out to it, just forward the entire payload, and then bubble up whatever comes back, right? Pretty straightforward. Now the reason for this just blind selector return is that both 1155 and 721, and I think maybe ERC 777, it's kind of been deprecated at this point. Don't really use it anymore. But these tokens can return those selectors, right? Or those tokens require you to return those selectors. So by doing that, you basically just default to like, if we don't know what this is, let's just go ahead and return the selector just in case. That way, if it's a token, we can actually just receive it by default, right? The way that this had to happen in Gnosis Safe was you had to like, I think they had to like extend their module, or that you had to like add a new module or like hook something up to it to make this work. Where like you could just like the company I was working for at the time that this happened, we were working with 777, and you couldn't transfer it to a Gnosis wallet because they didn't have this extension that like returned that selector from that function call, and it was kind of obnoxious, right? So this is basically just a long-winded way of saying like we just return the selector no matter what if nothing is set to it, just to like keep the tokens quiet and just allow them to like transfer these things to us, right? So yeah, essentially what this is doing in here, right? There's a lot going on here, but essentially what we do, this is pulling the selector from call data. We just like pull the first word, right? We need the first 4 bytes, but we can't just get that. Like we could do like, and operations and masking and all that. But instead what we do is we pull this word from call data and we shift it all the way to the right and then all the way to the left, because whenever you shift something, any bits that go out of range are dropped. So that means by shifting right and then shifting left, we actually lose everything except for those 4 bytes, right? Where it's with 4 bytes, that's going to be 32 bits. So that's like 224. Yeah. So we're shifting 224 bits so that only 32 bits are left, and then we shift it back, right? So that extracts our selector. We put that in memory, right? Now again, same thing as before, right? We can assume that memory at slot, or at index 32 is 0, so we can kind of just omit that, but there would be like an implicit 0 there. We go ahead and hash that, right? And we use that to pull the target from storage, right? So now we say like, okay, we've computed, the dispatch storage slot for the selector, and then we pull this value out. That's the target. Now, if the target is 0, right? Like I said before, we just return from memory that selector, right? The selector that we just put into memory. So that's like the easy way, right? If you don't have a mod set up that's supposed to like do something special with a 721 or an 1155 on receiving that token, we can just return that, right? It's no big deal. It's fine. But if the target is assigned, right? Like if it's not, we go ahead and return. But if the target is assigned, we go ahead and copy the call data to memory. You've seen this before a couple of times now. We delegate call, right? Where we, basically just forward, everything out to whatever this target is, right? And then we bubble it up, same way as before, right? So we copy return data. If the call is successful, we'll return it, and if the call is a failure, then we revert with it, right? So this is essentially like sort of like a proxy, right? Where you delegate call out to an implementation, no matter what it does, you just bubble up whatever it gives back, right? It's like very similar system to like what a proxy does. And so yeah, that's the core deck, right? So like it was shown here. The user can make a call to any of these functions. These functions go out to the ether deck. If it matches, or sorry, if it's like run or run batch, it'll go out to the target. But if a selector doesn't match, then we go through the mod and then we check this sort of register, this sort of like local mod selector registration, right? So that's the core deck. Do you have any like questions or anything you want to like dive into with this before we start looking at the mods?
The last part, the fallback, is really cool, GT. I've never seen this before. Like mimicking the signature is, it's pretty clever. I like that a lot.
Yeah, I appreciate it. It's such an obnoxious abstraction, right? Because at first I was just going to make like mods that allow you to like receive all of these different tokens, but then I was like, it's an extra delegate call and it's kind of expensive, so just figured like make it easy. Like because the thing is, right? Like if you want to do something special whenever you receive a 721, you can actually hook a mod up to it, right? And you can say like, I want this mod to like when it receives this, maybe like tip the person that transferred it to me or something, right? Like if you just do that and you set that target, then the target won't be 0. And so now you can actually go and do that. And then that's responsible for bubbling up your selector, right? But other than that, it's just an easy way to kind of get around that premature abstraction in a sense. So yeah, that's the core deck. Pretty, like I said, pretty bare bones, pretty minimal in terms of like its actual functionality, right? You just run a transaction, run a batch, set a dispatch, do that in batch, and then this sort of like fallback that can handle everything else. Now, in terms of mods, And I'll kind of quickly go through these because there's a lot of functionality that goes into some of the stuff. But first up is a bribe mod, right? So right now there's two different parties that you can bribe to run your transaction for you, right? First is going to be bribe the builder. Now this is like your classic, like if you ever worked with like Flashbots, right? A way that you can sort of conditionally run a transaction is like you can basically say, let's say you want to like execute some arbitrage, right? But you only want the transaction to execute if, let's say, the arbitrage is successful and you get like, X amount of ether as a profit, right? So what you can do is you do that arbitrage in your little contract, and then you have a little external call that essentially says like, take I don't know, 5% of the profits from this, and then send that to the Coinbase account, right? And what that allows you to do is you can actually send this with zero gas, like you send it with gas, but the gas cost is zero. And what that actually does is like the block builder will look at that and they'll simulate the transaction, and if there's a profit in it for them, they'll run it. If it's not, they won't, right? So by doing this, you can run a transaction that has zero gas value. If it's profitable, it'll kick back some of that value to the block builder. The block builder will see this is profitable, and then they'll include it in their block, right? This is something that like will benefit the block builder, so they have an incentive to put it in their block. But let's say your arbitrage fails, right? Let's say like somebody got in ahead of you, or like maybe the price moved in a way you didn't expect. You don't make the profit, which means you don't have enough to send to the block builder. Therefore, there's no incentive for the builder to include it, so they don't include it, right? They just drop it. And so that's basically what this function does, right? Like it's very similar to the run function. You can see pretty much everything here is the same except for this one step, right? And so what this does is, again, check that the runner is the caller. We copy call data. I'll skim over this for now. We do this external call to the target, copy return data, bubble it up, either return or revert based on the status of the call. But in between here, we can do this bribe where we say the Coinbase address receives this amount of a bribe. We don't send any call data. We don't expect any return data. We don't care about anything else. Just was this successful or not? We compose that with the rest of our success booleans, and like that's essentially it, right? Like very straightforward. It just says like, if this is profitable, send this bribe off, or just blindly send off this bribe, and if we have the balance for it, then it'll work. If not, then but yeah, so that's kind of the idea behind this one. It's pretty simple, pretty straightforward. The difficult one was bribe the caller, right? And so the idea behind this one was, what if I wanted to like create a transaction and put it in the mempool, like put it in a public mempool, where like I can still constrain that like it does my action, like what I want it to do, but like I want somebody else to run it for me, right? And I'll give them a bribe to do that, right? So what I can do is I can submit this to the mempool with like very, very low gas, right? Enough that like it probably won't get included for a while. A generalized front runner could look at that transaction, run it, replace the actually I don't even have to replace anything, right? They can just like simulate the transaction and see that if they're the caller and they run this transaction, they actually get a kickback, right? That's the bribe amount, right? And so like by doing that, they actually have an incentive to run your transaction for you to capture that bribe, right? And so that the way that we actually do that, and the way that we actually constrain that, it's actually going to do the thing that I want it to do, right, is we just have a signature, right? And that signature operates on the payload, the target, the call value, the bribe, and a nonce, right? Nonce, of course, is for replay attacks. The bribe is obviously the amount we want to give them because we don't want them to be able to increase that arbitrarily. We set the call value because that's going to be like the actual like value of the call. Target is going to be, of course, like where we're sending it, and payload is what we're sending to the target, right? So just skimming over like the majority of this for a second, right? Just like cutting that out, we can see it's pretty straightforward still, right? We're copying like the payload to memory, right? We're making an external call, right, to a target. We're copying whatever return data comes back from it, and then we conditionally return or revert with it, right? So the core is still the same. The difference is like, how are we validating that this is like correct, right? So the way we do that is we're going to copy the sig data or the signature data to memory. We'll make this like little static call, right? So this kind of makes the assumption, right? This static call out to 0x01, which is the EC recover address. So we're essentially assuming that the sig data is encoded out of the box the same way that an EC recover call is, because like that allows you to like really save like a lot of gas and like moving stuff around and save memory and things like that. So And of course, like if it's wrong, right? If the assumption is wrong, then like the EC recover just fails, right? So it's basically like a no risk assumption there. So you take this sig data, you copy it to memory, you send it off to the EC recover contract, right? You're going to get back an address. Now remember, static call or delegate call, they don't return anything but a Boolean, right? They just return this like success Boolean, which we compose throughout the call. The way you get the data that comes back is either through the return data copy down here, or you can specify these arguments in the call, right? So I can say that like, when I make this static call, I want the return data to start at slot 0 in memory, and I want it to be 32 bytes, right? And so by doing that, like when this call executes, the return data automatically gets copied to memory, which is cool because now we can just like load it from memory and then start running with it from there, right? So in this case, we're not checking if the caller is the runner. We're checking if the value that comes back from EC recover is the runner, right? So we have to make sure that whoever signed this thing is the person that's authenticated to generally run these transactions, right? So we check the sig data, we get this, we get this recovered address, and that's the runner, right? But now we want to make sure, like, like in this case, if you don't check anything else, you can just submit any signature that's ever come from the runner, and then you're fine, right? So what we want to do is we want to check the first word of the sig data, right? If we go to evm.codes, which is pretty goated website for just kind of like quickly looking at Ethereum stuff. EC recover is laid out in memory such that you have the 32-byte hash. You have these are like different size values, right? Like the V is like a small like 8-bit number, and RNS are like these big like big like field elements, right? But because of the way ABI encoding works, these are all padded out to a full 32 bytes. So you get one word that's hash, one word that's the V, one word that's the R, one word that's the S, right? So all of that stuff, again, we're assuming is encoded correctly, because if it wasn't, EC recover would fail. And then from there, we, let's see, where is it going to be? Yeah, actually, this is all it here. So we're kind of like taking advantage of like memory like more than once, right? So like this call data copy of the payload is used for two things. One, it's used for the actual external call, and then two, it's used for verifying the sig data, right? This is why the payload is the first thing in in the data of what needs to be signed. The payload is first because we're putting that there in call data, and we're going to use that both for the external call and for the signature verification, right? So we copy our payload to memory here. We store the so at the payload length, right? So at the end of the payload array, we're going to store the target, right? Full 32 bytes after that, we're going to store the value. 32 bytes after that, we're going to store the bribe, right? And then last thing we need in this list of things, right? We have everything except for the nonce, right? So we're going to load that nonce from storage, and then we're going to store that 32 bytes after the bribe, right? So we can kind of see like we store the target here, then 32 bytes after that, then 32 bytes after that, then 32 bytes after that. We're storing these things, right? This little intermediate step just allows us to cache the nonce variable to omit an extra storage read, right? So we read storage once, we cache that, and then we can use that in two different places here, right? So first is to put it in here and like validate that, essentially that the hash, right? So we call data load sig data.offset. That's like the first word of the sig data, which is from here, it's the hash, right? So we load the hash from call data, and then we essentially just SHA hash it, right? So we say this is, 96? So 96 plus the payload length, right? Because we have payload length. Then we have 32 bytes for the call value, 32 bytes for the bribe, 32 bytes for the nonce, which adds up to 96 bytes. So we hash everything together. We get the call data, we get the hash from the call data. We assert that those match. And then if that matches, we compose that with the rest of success, right? So we say like, okay, the signature is valid. It returns the runner's address. And then the hash of that signature matches, these arguments that we're laying out in memory here. And then after that, of course, we want to increment the nonce, right? So this like nonce slot here, and these are all defined in the dev docs, right? In this case, it's like ether deck Mk2.nonce. You hash that string and then subtract 1 from it. The subtracting 1 is is just like a way to basically make sure that nobody can like force a collision through like these like pre-image attacks and things like that. So like the SHA hash of anything -1 is like an unknown pre-image. We have no idea what what you could hash to get that value. You have to subtract the one to make sure that that's like not possible. But yeah, so we do all of that, right? We do all of this like signature verification stuff, right? We execute our call, we're doing all of that bubbling up, and then right here we bribe the caller. So whoever the caller of the transaction is gets the bribe. And that's like this line right here is what allows a generalized front runner to realize that if they just submit this transaction themselves, they actually get a profit, which is equal to the bribe, right? So you get your action, they get their bribe, and we all go home happy. And then of course the nonce function, essentially just loads that slot, right, and then returns it from memory. That's our bribe mod. Thankfully, most of these are going to be like way simpler than the bribe mod. That one's pretty complicated because of the sig verification, right? But yeah, so in the creator mod, this allows you to create contracts. From the Ether deck. Create just uses the standard create opcode, right? So again, make sure the runner is the caller. We're going to copy the init code to memory, from the call data. We'll run the create, opcode, right? So create the contract. Then we just want to assert that like the deployment is non-zero, right? So is zero is like a way of like sort of flipping the Boolean, right? So like if deployment is zero, but if the deployment is zero, then is zero deployment will be one, right? But then like is zero flips that one to a zero, right? So it's just a way of saying like I want the deployment to be non-zero, right? And yeah, then we just store that in memory, right? And so if it was successful, right? So if both the caller is a runner and the deployment was successful, then we return that. Otherwise, we revert, right? Create2 operates basically the exact same way. The only difference is you get a 32-byte salt. And by doing that, you get deterministic deployments, which means you can do those like, leading zeros, or like you can have like hex, like certain hex characters as like a prefix or a suffix to your address, which is pretty cool. And then compute2 is essentially just, it's a view function, right? So you don't have to pay for this. This is just a way to like get an idea of like what is the create2 gonna output, right? Given a salt and an init code. So you can actually like, you can deterministically like deploy this, so so you can pre-compute like what the deterministic deployment will be, so that you can know that like it's actually like correct, and you didn't just waste like a ton of compute for like no reason, right? That's the creator mod. Next up is going to be the flash mod. So this one gets hella complicated. I'm not going to go like super in depth because there's like a lot of memory ops in this one, but essentially like what this is, right? Like for compliance, you have this max flash loan, right? That's a core part of the interface. Flash fee, which takes a token and an amount, right? And so you just tell it like what amount to return, or what the flash fee is for like a given amount, and then the actual flash loan functionality, which we can actually look at the differential to get like a high level view of what this is first, because this one's pretty out there. So max flash loan, pretty straightforward. If no, I'll get to that in a second, actually. But let's just like look at this really quick. So, in here in the flash loan, right, we make sure that like this is something that's assigned, right? So make sure that like it's a token that we're like allowing to be flash loaned out. We compute the fee for the given amount that they want to flash loan. We'll transfer the tokens out to the receiver. We'll do this callback, which is like on flash loan, right? We call that out to the receiver. And then after the call, we transfer from, where we pull back the amount plus the fee, right? So it's like a very like core, simple, like pretty elegant way to do like a flash loan ERC. So I really like this. I wanted to like do this myself, but this is the core of like what's actually happening, right? And the way that you sort of assign what the flash fee is, right? The way that you're assigning the flash fee to a token, right? Where you say like this is the factor of this like flash fee that says like if I don't know, if you want to take out a loan of like, let's say like 10 tokens, right? Then it's like 1/1000th or 1/10,000th of it, right? And so you can do that like computation to say like, okay, this is how much the flash fee is going to be. And so the assumption that we're operating on here, and sort of the assumption that the ERC operates on, is that if the flash fee factor is set to 0, then we can assume that there's going to be like no flash fee for that token, right? That like it's like basically like the idea is that there's nothing assigned there, so we don't want to like loan that token out, right? So you have to go out of your way to say which tokens you want to allow flash loans on for one reason or another. But Yeah, so you can set the flash fee like factor, right? And that factor, you just make sure it's like smaller than the divisor. And then we just store this at this this like custom thing, right? It's essentially like doing the same thing as Solidity's storage mappings, where you have like the key and then you have the storage index. It's doing the same thing where, like, in this case, the token is sort of the key, and the storage index, right, is like the hash of either Deck Mk2 dot flash fee slot index -1, right? So again, we're making sure that the storage index itself has no like known preimage, and then we're just concatenating those together and computing it just like any other mapping, right? And yeah, so we can kind of just use that, right? That flash fee factor that we're like loading. We can say, like, if it's greater than 0, then like the max flash loan is basically the entire balance, right? If it is 0, then we just say it's 0, right? Like you can't loan out this, like you can't get this token lent out to you. Flash fee, is basically just doing the computation, right? And so all that's pretty straightforward. And the way this is actually like working, let's see here, is we're basically just doing all the same stuff as there, just like with a few like less checks, right? So like, this is our storage slot here, right? We can see like this is what it's computed as, but we set the flash fee factor, right, by basically just making sure, again, we want to make sure that that the factor is not greater than the divisor. We want to make sure that the caller is the runner, right? So we do that check. We store these things in storage, or sorry, store them in memory. We hash them together to get our slot, and then we store the factor there. And then pretty much everything else after that, right? Like any interaction with this storage slot, you'll see like we do that. We kekak hash it, and go from there, bubble up, blah blah blah. Again, there's a lot of assembly in this one, so we're not going to go into it today because I think we are getting pretty close to time. But that's the core of the flash mod. Is allows you to just flash loan arbitrary ERC20s. The flatline mod, this is our dead man switch, right? This one's straightforward. It only has 3 functions. One, sets the contingency, so it says this is a receiver. If I don't check in by this interval, then this is the receiver that becomes a new runner on this contract, right? So again, pretty straightforward. Make sure the caller is the runner. We essentially, we're going to bit pack this one. So we bit pack it, which is documented here. We bit pack it where you have the receiver is the upper 160 bits, the interval is 32 bits, and then the last update is 64 bits, right? 64 bits takes into account the 64-bit timestamp that we're going to need in 2038. And then the interval, we can more or less assume that it's probably going to be less than some 60, 70 years. So, 32 bits is more than enough, for a simple deadman switch, right? Because the interval is not just after this timestamp, just release it out the next person. It's you have to check in within an interval of, some 70 odd years, right? So I think that's a pretty reasonable, thing to get this all packed into a single slot. But basically that's what this is doing, right? So we're packing all this stuff together into a single slot. And we store it at, again, the SHA hash of, EtherDeck Mk2.flatline slot -1. Checking in essentially is just like you pull these values from storage, right? And you basically just update the last update, right? And because this is the last 64 bits, we can actually do this in like a really simple way, where we basically just mask out, that last update. So we still have the receiver in the 32-bit interval, but now the 64 bits at the bottom are all cleared out. And then we can just put in the new timestamp there, right? We can assume that, the timestamp won't exceed U64 for some several billion years. So I think this is more than enough, to make sure that it all fits. But yeah, so basically all that does is it just updates, the last update for you, right? Everything else stays the same. And then finally we have the contingency. Oh, by the way, one other quick note. If the interval is set to 0, the contingency is inactive, right? So no matter what, even if you have a receiver set, even if there is a last update, as long as that interval is set to 0, there's no way that the contingency can happen, right? So if you want to deactivate this for some amount of time, you can always just go in and set the contingency, interval to 0, right? And then you're good to go. But yeah, so what we're going to do, right, is we're going to pull the value out from storage, right, using that pre-computed storage slot. We get the last update, by doing this little masking operation. We get the interval by doing a little bit shift. We basically take that interval, the 32-bit interval, we shift it 64 bits to the right, and then we mask that with, the max U32. And so the check that we're doing here, right, is we say if the timestamp is less than the last update plus the interval, right? So like if the last update plus the interval is like not come to pass yet, right? If the timestamp is less than that, or if the interval is set to 0, then we revert, right? You're not allowed to call this function and execute the contingency unless the timestamp is greater than the sum of the last update in the interval and that the interval is non-zero. That's the only case in which this succeeds. And so what that does, right? If you pass that check, if the contingency is like ready to execute, then for one, you update the runner slot, right? So this little like shift right operation here, this basically just takes the receiver and just shifts it 96 bits over to the right, right? So it shifts that, and then we have that we have the address, and then we can just put that straight into the runner slot. No need to mask because it was the upper bits, right? And then we basically just reset the contingency slot, right? So that's just reset to 0. So that's the flatline mod that allows you to transfer the ownership. And I think we're actually coming up on time. Do you want to cut it here, or do we want to
Yeah,
run through these last couple
let's
ones?
talk about testing. Obviously, when you write contracts in general, testing is super important, but especially when you're writing inline assembly. So if you can
Mhm.
walk us through the testing infrastructure that you have, it would be
Yeah.
really
So
interesting.
right now, so right now there's like three sets of tests that we have. There's another one that I want to do. I want to set up invariant tests as well for obvious reasons, um, or sort of like stateful fuzzing tests. But right now, what we have is we have unit tests that test a handful of cases, basically like every like explicit code branch we want to test. We have the fuzz tests, right, which are just very basic. Just throw these like random values at it, and then if certain thresholds are met, we throw. Otherwise, we don't. And then we have differential tests, right, which is we're basically de-optimizing every single mod and the ether deck and the registry and everything. And then from that de-optimized thing, we basically just fuzz both of them side by side and just assert that their behaviors are the same, right? So our like core test, for example, the bribe mod, right? We have we test the nonce, we test bribe builder. What happens if you bribe the builder but you're not the runner? What happens if you don't have sufficient balance? What happens if um, the target reverts? What happens if you bribe the caller? If the sig data is invalid, insufficient balance, and then we do like the fuzz test on here. And then in the differentials, we have the differential implementation, which tries to minimize for assembly. There are like some cases in which assembly is just necessary, like arbitrary storage rights, or if we're just like fully bubbling up like return data. But it's not necessarily like structured in a certain way that we end up bubbling it up like that. This is mostly just for like interface matching, but yeah, essentially like we have all of the high level logic built out with as little assembly as possible in pretty much any of these, right? And so what we actually do is in the differential tests, we do all of these all these different parameters that go to a fuzz test, right? And so we basically just run everything side by side. So this one makes sure that the mass revoke mod can revoke ERC20 approvals, right? So we like loop through because there's like a lot of like really complicated things with like fuzzing addresses and fuzzing like addresses to call to. I actually found that like doing vm.etch is like a huge pain because you can't etch onto certain addresses and there's like precompiles and like a lot of really unexpected behaviors. So instead, what I actually found is it's better to when you want to fuzz against, let's say in this case, like a mock ERC20, but you want the addresses to be random every time, you can actually just add like a bytes 32 salt into your arguments in the fuzzer, and then you can use that salt which does a create to, right? Which like while the deployment is technically deterministic, it's deterministic to that salt, which means that we can actually just go and fuzz that salt and get different deployments for everything. And these loops, we just like rehash the salt like over and over again. So we basically get like random values like every single time, right? Which is nice because then you get like a wider array of like what addresses are being called and things like that. We're doing some basic like precondition checks, just making sure like everything is set up good to go beforehand. And then we go through and we say like, okay, in this case, like I have this little like length mismatch thing that if we want to force length mismatches, then we can do that. And I'll explain why I'm using a boolean and not just two arrays in a second. But yeah, basically like if these like revert conditions are true, then we'll do an expect revert on both, right? Otherwise, we'll run both, and then we'll just do these assertions on both, right? Usually in some kind of loop. Right. So there's two weird, like non-standard things here that like don't really make a lot of sense on the surface. But one is the length mismatch, which says like, so the ERC20 approval thing, you're revoking implementation really quick. Yeah, so you give it an array of tokens and and spenders, and you want to like one of the conditions in that, right, is like the links have to be the same, right? The problem is like if you just give two arrays in the fuzz arguments, then like there's like all of these cases in which the links don't match, and so like a very small subset of all of your fuzz tests actually have matching links, which means that like very few are even going to pass, which like really limits your ability to check the success cases as well, right? So what this does is by having this Boolean, we're generating the token addresses on the fly, and the length of it, right, is either the same as the spenders, or if this Boolean is true, it's the spenders plus one, right? So what that lets us do is it allows us to go 50-50. Like, are the links the same or are they not? So you get a good spread on those. And then same thing with runner versus actor, right? The actor is the person that's actually executing the call, and then the runner is the actual address that's set as like the authorized account. Again, if we just allow these to be random, there are very few cases in which the runner equals the actor, right? Now, the Foundry fuzzer will force them to be equal every once in a while, but you're not going to get the coverage that you need for that. So by doing this little Boolean, like, is the runner the actor, we can actually like overwrite the runner, right? And like it basically makes it like, I guess slightly more than 50-50, like very slightly, but essentially like 50-50 is the runner the actor or not. Right. And so just little things like that just help you get like more coverage. It allows like issues in your fuzz test to show up much sooner. Right. Like the default right now is like when I'm actually like actively developing these things, I usually do 256 runs, which really isn't that much. And then whenever I want to like just brute force, just tank through all of it, then I'll set it to like 10,000, right, and just like walk away and go get lunch or something, right? And let that run itself through, right, so that you can see like in these like very very long range cases, like do things work out? Because sometimes it takes like, I mean, there were edge cases in this that took me something like 200,000 runs to hit, right? Like it took a very very long time to get some of these edge cases, to come out of the code. So there's a lot of stuff like that, just to kind of like speed up that process to make sure that we're getting like good coverage on the success and the revert cases. But yeah, we have differentials of everything. We have differential tests of everything. Handful of mocks that can kind of do different things, right? Like your mock target, you can tell it whether or not to throw. Your mock mod, I think you can tell whether or not to throw. And so you can like test little cases like that, here and there. So as of right now, like all of the mods are kind of being tested in a vacuum, which is obviously like kind of, I mean, it's kind of a problem, kind of not. Like it's good because you can isolate what are the conditions of like the exact mod. But then you want to be able to test it alongside the deck, right? So like there is like a plan for this like huge test of like you hook up the deck and then you hook up every single mod to the deck, and you want to make these assertions like, can anything at all accidentally overwrite like a critical storage slot, right? Obviously storage mod can kind of just write whatever. So, there's like a special case for handling that, but like everything else, like it should never ever collide any of these storage slots. That's like incredibly important. And then there's just other things too, right? Like, provided that like the runner is the one that's always calling it and the runner never hooks up a mod that has self-destruct, there should be no code path in which you can delegate call out to something that like self-destructs, right? So there's a handful of things like that I want to test by like hooking everything up together as well. And then also one other thing that I want to look at is the primitive team, Primitive Finance, they came up with this thing called Arbiter, which is like basically just this chaos actor, right? Now they actually designed it for like AMMs and things like that, right? But like it is still like a pretty cool piece of software, and it's like this sort of invariant test in a sense where you can kind of just throw a bunch of actions and actors and conditions against these different things and like see how they behave, right? So definitely gonna be spending some time on that.
I had them on the podcast actually.
Oh yeah, that's cool. Were they talking about Arbiter?
Yeah. Yeah.
Nice.
Yeah. It was really interesting.
Yeah, it's cool.
JT, this was amazing, man. I learned a ton of assembly tricks. I'm a Solidity guy. I never did anything production grade in inline assembly. I played around a little bit with Huff, but yeah, this was I learned a ton for sure. So thank you for taking the time. I know you're a huge open source guy, so link to the repository is gonna be in the description below. If you wanna contribute, reach out to JT. Probably GitHub and Twitter are the best places, right?
Yep, GitHub and Twitter. Twitter is jtriley_ETH. GitHub is jtriley-ETH. And then also, Discord. We're in the Rip Jesus Telegram, or sorry, Rip Jesus Discord. That's a pretty common place to talk about Foundry stuff too. So, yeah,
Awesome.
if
I'm
you guys
gonna
want
put
to,
all these links in the description below. JT, thanks again for taking the
sweet.
time, man. This was super cool.
Yeah, thanks for having me.
Okay, guys, see you in the next one. Bye bye.